There's a saying, if you have a hammer, the whole world looks like a nail. And so I've been studying manufacturing systems for a long time, so everything looks like a manufacturing system. Anyway, there we go. Okay, I was very lucky that my friend Larissa provided a lot of really nice pictures, examples of manufacturing systems. This is not a typical manufacturing system. They're making airplanes. Here you have a whole line of planes. They're busy or workers are busy doing operations on them. This one is evidently done, and I don't know how it's going to fly away, but I suppose it will. Okay. Oops. I could put some other things. Let me give you a case study. This goes back a long way, but I'm familiar with it. HP makes printers. Actually, these days, HP doesn't so much make printers as use external third-party manufacturers, so-called contract manufacturers, to make its printers. But this was sort of the last thing that they were making in any great volume. This is back in the days when inkjet printers were just coming on the market. One of the things that the marketing people tell us is that when a new product comes on the market and they anticipate that it's going to become very, very popular, that a manufacturer wants to get as much of the market as it can very early, because people have a kind of brand loyalty. So the idea was to get the stuff out as fast as they could and get people to buy this stuff, these printers. So the different manufacturers were competing for market share, and the manufacturers could sell basically all they could produce. So the demand was greater than production capacity. And so the big problem that they had was to try to increase their production capacity as much as possible. There are other requirements. There are other objectives that factories have besides just maximizing production. But that was the case here. So we're going to focus on this Eclipse thing. They invested. Did I skip a slide? Yes. Okay. So they had certain objectives. It's very important that they maintain quality. That's the most important thing. Because if you sell shoddy products, then nobody has any brand loyalty. They wanted to meet this increased market demand and increase their market share, and their target was to produce 300,000 printers per month. They had to meet profit and revenue targets. They did not want to be hiring and firing people. They wanted to keep employment stable. Oh boy. Sorry. I have to turn her off. They were, at the time, producing 200,000 printers a month manually. And they wanted to replace that with the manual workers with automated factories, with an automated factory. So here was the whole thing. This was the production of one part of the printer, not the whole story, the so-called print engine. So that's where the print came out of the ink came out of the nozzles and was shot onto the paper and so on. So this was very important and very precisely made part of the printer. Buffer is a storage area. The final assembly is when they put the whole printer together, the external parts and so on, and then finally packaging and shipping. So here's where you see the sort of multiple stages that the products go through in the factory. Okay, this is a very schematic representation of how they had designed the system. Now what's going on here is that parts would come in through here, and they produced this first thing, which is represented in gray, and that was sort of a chassis that everything would be put on, and other things were connected there. Then there's a series of operations. It's traveling this way through the system. So there's a series of operations that are taking place here. And then here's another sub-assembly that system that's producing something that we're representing by little squares. So now we have squares on these gray things, and they're traveling around, getting more operations. And then this one produces little circles and continues. And this one produces little triangles. And then we're done. And here's the final product, or at least the final product that's going on to the next stage of assembly. So one of the main ideas that they had at the time was to essentially have zero buffer space, meaning zero inventory, zero space for inventory. That was, these days people talk about lean manufacturing, which means small inventory. But in those days, people thought that you could get away with zero inventory. And we're going to look later at the consequences of that. So, they estimated that the machine efficiencies were about 99%. The efficiency is the fraction of time that a machine is in operational condition. The operation times were estimated to be exactly 9 seconds and constant. So based on that and the total number of hours that the factory would be operating and the number of copies of this, there were 2 copies I think of this system, they estimated they could produce 370,000 units per month, which was great. They needed 300,000, so that would work. But these machines were produced elsewhere, produced by vendors, and they started installing them, setting up the factory and testing out these machines. When the first 2 machines were installed, they discovered that the efficiency was less than 99%, and the operation times were variable, often greater than 9 seconds. Now, they weren't much less than 99%. I forgot what the number is, but it was certainly more than, I'm pretty sure it was more than 98%. But the problem was that there were something like 100 operations taking place. And without having any excess inventory space in the system, the concatenation of all these machines possibly going down for 1% of the time each would very seriously impact on the production rate of the line. In addition, the operation times were variable, often greater than 9 seconds. So as a result, they then estimated that the production rate would actually be about 125,000. So that's not good. Now they knew they had to make some changes. They were not allowed to add labor or redesign the machines. The point of this was to reduce labor so they couldn't add labor, and redesigning the machines would take too long. What was possible was adding a small amount of buffer space within the system. However, they didn't really know how to do that. They didn't know what, well, I'll get to the answer in a minute. Very fortunately for them, a graduate student of mine was there at the time, and we had been studying just this issue. And he did a little back-of-the-envelope calculation and figured out just how much additional buffer space would make a difference. So, the new version of the system looked like this, and if you think about what the old one was, you can look back and look at the old one, there's a lot more space in the system. So the same operations are taking place, but now with all this space, if one machine fails, the other machines can keep working. In the system with no buffer space, if one machine fails, they all have to stop together. Okay? One of them is down, but the others are forced to be idle. So that's where they lost all their production rate, all their production. So we had, first of all, these extra empty pallets available, but more importantly, we had in-process inventory space around here. We just increased, they increased the size of this, of the track that the parts were running around. Essentially, these are buffer areas, and the important thing was that the buffer sizes were large enough to hold about 30 minutes worth of material. In other words, 30 minutes worth of production. And that's important because the mean time to repair the machines when they would go down would be something like 10 minutes. Okay? So that was enough so that most of the time when a machine failed, it would not affect other machines. We're going to make all that precise later. So this led to increased factory capacity, not quite to the 300, but 250,000 per month. The capital cost of making the changes was about 1.4 million. They estimated that the incremental rewards, incremental revenues was about $280 million. because that had to do with how much additional stuff they could sell as a result of making these changes. Plus, I think, plus all the extra ink cartridges they could sell and so on. So the research results, the impact on MIT is that some of these research results, well, became known and were incorporated into some courses, basically mine. There was an MIT spin-off called Analytics Operations Engineering, which was just last month acquired by McKinsey Consultants. So, success. So that should motivate you. Now we're going to talk about what's going on behind there. So the focus of manufacturing system engineering is on the flow and storage of material. Given the product and the process, we think about the design and operation of new manufacturing systems and the analysis and improvement of existing manufacturing systems. So in the whole, I guess, product realization universe, it fits in here. So basically, how do products originate as a bright idea and then end up getting manufactured? Well, somebody designs the products. And when the products are designed, somebody designs processes to make the products. And then somebody has to figure out what machines are needed to implement those processes. And then we have to figure out just how much buffer space is required. And when there are choices to be made in real time, somebody needs to figure out what choices you need to make. So should a part go here, should a part go there, which part should be produced next if you have a choice in the different parts. But this is not a straight line process. And this, of course, is not an operational block diagram, but you can see that what's going on here is that once you get to the end and you think you have something reasonable, you have to evaluate it by means of some kind of evaluation method, often simulation, often less often analytical methods. So the question of are the costs and the performance satisfactory? And the answer is no. If the answer is no, then you have to go back and change something. So, as I said, this is not an operational thing. And you change all of these things. You consider changing all of these things, including the products. One of the things that's very important is that the design of the product should be, in part, influenced by the constraints imposed by manufacturing, or the difficulties that manufacturers encounter. Years and years ago, manufacturers used to complain that the designers would throw the design over the wall, and then they would just have to make it, and no feedback went back. But people are sort of a little bit more aware of the need to do this. So manufacturing systems is in this little red box here. Okay. The issues that manufacturers are confronted with these days is that new products are introduced very frequently, all the time. The lifetimes of the products are very short. So as a result, the lifetime of the processes can be very short. So that can lead to short factory lifetimes. At least factories could be built or rebuilt, or they have to be reconfigured frequently. And in the days when factories and products would last for a long time, you could watch them in operation and then see where problems are occurring and then tweak them a bit to improve them. People used to talk about continuous improvement. And you still need to do that. But you also have to get it right the first time. And so that's what the goal of this work is. Okay. Quantity, which is what I'm going to focus on, is how much you make and when you make it. Quality is how well you make it. I once heard a definition of the difference between manufacturing quality and design quality. We're talking about manufacturing quality. Design quality is the effort to give something that will make customers happy. And manufacturing quality is the effort to not have something which makes customers unhappy. Okay? So we're going to think more about that. And what makes customers unhappy? Products that fail. Products that are not delivered on time, and so forth. Okay, this is going to be a very abstract and fundamental view of what a manufacturing operation is. So there was no details here, but it's the operation in context. To do an operation, you need to have a part coming in, and you do something to it here, and then you have the part going out. And the purpose of the operation is to make a transformation on this thing to make it closer to what you can sell. Make it closer to useful. In order to do that, you typically need a machine. You sometimes, but not always, need an operator. Sometimes you need consumable material like coolant fluid for metal cutting or chemicals for semiconductor manufacturing. And there's waste that's generated, and you have to take the waste away. Okay? Now, you can't do the operation until all of these things are present. In particular, if the part is not there, certainly nothing's going to happen. If the operator is taking a break, then nothing's going to happen. If I include these things, if the mechanism to take the part away and the place to put the part are not available, then you can't do the operation, and the same for the waste. So nothing happens until everything is there at the same time. Now, the problem is that because of all these random events that I'm going to talk about that happen in the factory, it's hard to do that. Also, the complexity. It's hard to get everything together simultaneously for all the operations that are taking place. So you have to decide what's going to be waiting. You want to minimize the waiting to the extent that you can, but you also want to distribute it in a way to have the least impact on the factory's performance. So whatever doesn't arrive last must wait. So let's go back there. If the part is not there, then the machine is sitting idle, the operator is sitting idle, we're not consuming anything, but it's there and so on. If the machine were down, then the part would be sitting idle, and the operator would be waiting around and so forth. We'd have somebody else come in and do a repair. So inventory is the word for parts waiting. Capital underutilization is machines waiting. And an idle workforce is when operators are waiting. Okay? So which is better? Which should we want to wait more? Okay, rhetorical question. The answer is, it depends on the context. Sometimes if the raw material is very expensive, but the operations that you're doing on it are cheap, then you don't want the raw material to be waiting. You might be willing to have extra copies of the machines, things like that. Okay. So my focus in this is variability. Oh, I forgot to highlight my important statement back here. Variability is the enemy of manufacturing. And in fact, variability is the enemy of product design, product realization. Because even in designing products, you design products to work well in an uncertain environment. So variability is something that happens all the time. And what engineers in general have to do is to somehow mitigate the effect of this variability. So uncertainty is incomplete knowledge. For example, who's going to win tomorrow's election? We have incomplete knowledge. Variability is change over time. Randomness is a certain kind of incomplete knowledge that we can quantify and for which we have a mathematical theory, and we make heavy use of that. Improvements in the design and operation of a manufacturing system should reduce the variability, uncertainty, and randomness, or reduce the sensitivity of the systems to variability, uncertainty, and randomness. Okay, so where does all this uncertainty come from? Well, factories are full of random events. Machines fail at random times. Customers decide to change their orders. They cancel something, or they increase an order, or they want it earlier, or they're willing to take it later. We do have quality issues. Sometimes a part fails inspection, and we have to decide what to do. We can rework it, or we can scrap it. There's also, of course, human variability. And the external economic environment is uncertain. There are various variations of demand. Sometimes suppliers don't produce when you expect them to. Prices and costs change. So the factory has to take all this stuff into account somewhere or other, either be robust to it or react to it. So factories have to be designed and operated to minimize the creation. The creation of uncertainty comes from machine failures, for example. So you have to make machines so they don't fail too much or they're easy to repair. Propagation we're going to talk about. Amplification I'm not going to say much, but basically a small change in one place can sometimes propagate through the system and grow as it propagates. That's when you have complex scheduling and you have deterministic computer programs that do the scheduling for you. Okay, what I want to do is to prove a statement that I'm going to make, which is that variability causes inventory. Okay? So, to do that, first I'll look at a no variability situation, and then I'll inject variability in there, and you'll see where the inventory comes from. So we have a tank here. Imagine that we have water flowing through the tank, but of course this is analogous. It's supposed to be analogous to a manufacturing, to a factory, where the tank is going to be a storage area. Now, suppose that I've got water coming in at this rate of 75 gallons a second, and water can go out. The pipes are big enough to let the water go out at 75 gallons a second. And I start the tank empty. Well, the tank is always going to be empty, except for a little bit of splashing here and there. Okay? So there's no variability. So there's no inventory. Now I'm going to add valves to the tanks, to the tank, to the pipes coming in and the pipe going out. And these valves are kind of unreliable, or for some reason, they go on and off at random times. When the valve is open, we can get 100 gallons per second going through. When the gallon is closed, we can't get anything going through. But the valves are open 75% of the time. So 75% of 100, that's 75 gallons a second. It should be just like what I just described. No difference. Let's say the average period when the valve is open is 15 minutes. The average period when it's closed is 5 minutes. So the average flow through the tank is going to be the 75 gallons per second. So, no change, right? Well, in fact. Now we have a bunch of cases, and this doesn't list all the cases. This is only a handful that I can put on the slide. If both valves are closed, then the inventory, whatever is in there, stays constant. Nothing goes in, nothing goes out. If they're both open and they're running at 100 gallons a second, then again, both the level of the water in the tank doesn't change. But if the downstream valve is closed and the upstream valve is open, then water accumulates, goes up. The other way around, water goes down and can even empty out. Okay? So because of this variability, because the valves are opening and closing, and the important thing is that they're opening and closing in an unsynchronized way, we sometimes have water in the tank. Okay? So, there's never any water in the tank when the flow is constant. There's sometimes water in the tank when the flow is variable. Two conclusions. First of all, a very general conclusion. You can't always replace random variables with their averages. Sometimes you can, sometimes you can't. It depends on the context that you're looking at. And, most importantly for me, variability causes inventory. Okay? So then the question is, given, see, this is a manufacturing systems course. It's not a machine design course, or rather lecture. So I can't do anything about the cause of those valves going open and closed. What I can think about is how large a tank I need. So the tank is a buffer, and a buffer is just a storage area. And here's a machine that's doing some operation on these strange objects. And this is Larissa, do you know, is this the input buffer or an output buffer? Doesn't matter. So these are a bunch, let's say it's an input buffer. These are a bunch of parts that have been delivered from upstream, and they're waiting for an operation on this machine, and here's a robot that's going to pick them up and put them in the machine and so forth. Okay? Here's something else. Evidently, this is a factory, a carrier air conditioner factory, and we have these machines that are flowing down the line and workstations here, but we can also store the machines on these conveyors, on these roller systems. Okay, so that means these guys are probably doing different operations. So when this guy finishes his operation, this thing flows down to the next guy, and he works on it, and so forth. Because of this, we can store some things on the conveyors, and so they don't have to be perfectly synchronized. Here's a great big storage area holding lots of stuff. I have no idea where this comes from, but you can see that in some factories you can store a lot of inventory. That's not good, generally. But no doubt they have their reason for that. Here's more. These are storage racks for small parts that are getting assembled probably onto some kind of electronic assembly. Here's an automobile final assembly factory. This is a conveyor system carrying these car bodies. They're going down to the line. Down here, people are going to be adding parts to the cars as they're going through. And these also represent some storage as well as transportation. So sometimes the storage and transportation are the same system. Okay. Now let's get to be a little bit more mathematical. And I want to talk about a queuing system. Anybody hear of queuing theory? If you ever take any operations research courses, you'll see a lot of that. Queuing theory describes the behavior of people waiting for service. That's the origin of it. A very simple thing, but it applies in a great many situations. So people arrive at this queue at rate lambda, and the operator does some service for these guys at rate mu. Okay? So for this slide, I want to think about deterministic arrivals and deterministic service. So in fact, the service time is always exactly 54 seconds, and customers arrive once a minute. No variation. Okay? So here's a graph that shows the number of customers in the system at any given time. So here's one guy that's being served. The first guy shows up at time 0, and he's being served, and then service is complete. The operator takes a 6-second break, and then the next guy shows up, and so forth. So with no variability in the system, there's always either one person or nobody in the system, and the average number of people in the system is 0.9. Now, let's make it random. And if you don't know what all this exponentially distributed stuff is, don't worry about it, where there's MM1Q. But this is the simplest kind of queuing system, where the customers arrive at random in a certain specific way, and the service time is also random in a certain specific way. But again, the rate of arrivals is lambda customers per time, and the service is, you can say that's mu services per time, or the average service time is 1 over mu. We're also going to assume that there's no limit to the waiting. Well, now it turns out that the situation is completely different. The number of customers in the system now varies over time, and it's not 0 or 1. So, starting at time 0, the first customer doesn't arrive for a while, but then he arrives and service starts. And then a second customer arrives. So now there's one guy being served and a second guy in the system. And then the service is completed, and then the server is working on, the service for the first guy is completed, so the server starts working for the second guy. But then somebody else arrives, and then somebody else arrives again, and so on. So the number of people in the system go up and down at random. So I'm using the same averages, that's what all that says. But now the average number of customers in the system is 9, not 0.9. And in fact, it's better illustrated on the next graph. Here's 9, okay? This is the number of customers in the system, and this is time. And you can see that it can get to be quite a bit larger than 9. 9 is just the average. So this randomness is an issue that factory people have to worry about. Now, just to give you just a hint, the mathematics for analyzing that involves creating what's called a transition graph. N is the number of customers in the system. When one customer arrives at rate lambda, when customers arrive at rate lambda, the number goes from n to n plus 1. Or when you have n customers in the system, when 1 is served, and that customer departs, and then you go from n to n minus 1. So this is a very simple Markov chain. At 0, nobody can depart, so it stops here, but it can go off to infinity if we don't limit the amount of waiting area. And based on that, we can calculate lots of things. In particular, we will define rho as lambda over mu. Now, in this context, that rho is 0.9. So that's called the utilization of the system. The average number of parts of the system, take my word for it, is given by this, well, it's two equivalent forms, rho over 1 minus rho, or lambda over 1 minus mu minus lambda. If you want some of the details, you can go to this website, which is the stellar page of 2854. So, there's something important called Little's law, which is L equals lambda W. I wrote this two different ways. N bar is sort of the typical way, it means the average value of n. And L somehow was also used, so that's why it's written this way. P of n is the probability that there are n people in the system, and this is just the expected value expression. So based on Little's law, the average waiting time is 1 over mu minus lambda. Okay. Now, that's only if rho is less than 1. Remember, rho is the utilization. It's the ratio of lambda to mu. It's lambda over mu. If rho is less than 1, lambda is less than mu. So this makes sense. This gives us a number. If rho is greater than 1, we're going to see what happens later. Basically, you don't have this average. In fact, over time, you get more and more people waiting. And we'll see that in a simulation later on. So let's look at W as a function of lambda. And here I'm going to choose mu equals 1. And that formula gives you this. And what that's saying is that as long as lambda is a lot less than mu, or rho is a lot less than 1, the utilization is a lot less than 1, then everything is pretty nice. There's not much stuff in the factory on the queue. But if you try to push lambda too hard, the number of people in the system go to infinity. Okay? And I'm sure you've been on queues like that. In fact, that's why rho is called the utilization. When rho is less than 1, the factory is not fully utilized. When rho equals 1, it is fully utilized. When rho is greater than 1, the factory is not working. You're attempting to do something which is not going to work. So, I have a problem here. Suppose I want lambda to be 1.5. I can't do that. So what I can certainly do is increase mu. For example, I can get a faster worker or a faster machine that's doing this. And I'll show you that on the next slide. But even suppose that I'm perfectly happy with lambda equal 0.98 of mu, but still I don't want this huge amount of waiting time in there, because, you know, if it's people standing on line, they're getting annoyed. But if it's delivering products to customers, the customers are getting annoyed, and that's bad for business. So, if we increase mu from 1 to 2, we get a graph that looks like this. And there are two important things that are interesting about this. Well, one thing that's obvious and one thing that's not so obvious but very interesting. The obvious serious thing is that we've increased the capacity, so now lambda can be much larger than in this case. It can be almost 2. But the other thing is, where if lambda were 0.98, when mu equals 1, we're up here someplace. But now we're only down here. So by increasing the capacity of the factory, we've reduced the effect of the variability. Okay, so there's a very important trade-off here. The people who invest in the capital, people who build the factory, would like you to have very high utilization because they want their money to be productive. And the more money you put into a factory, the longer, in effect, the lower return on investment and the longer it takes to get your money back and so on. So you want that capacity to be very large. So you'd like, I mean, you want the capacity to be very small, because if it's larger than the minimum, then you're kind of leaving things idle. But the problem is, if you operated like this and you wanted to have, 0.98, then you run into bad performance. If performance is very important in terms of lead time and reliability, then you want to have extra capacity. But you have this trade-off. And that's sort of very fundamental. That's why I brought up this issue. I think, yeah. Okay. Any questions about this before we start on something else? I'm getting a lot of head shakes, so therefore no. Okay. Let us actually build the factory, shall we? To do that, we need some worker volunteers. 2 brave people. Come. You too. Make a note of who it is, give them higher grades as a result. Or at least write a good recommendation for them. Okay.
The first employees in our underway factory of the future.
This is more of a factor of the past, but that's okay. Okay, so please take your seats.
Take your seats.
Okay, so Dave, you want to describe what we're making here?
Sure. So we're running a 2-machine line, and they're going to be machine 1. We're going to build 4 blocks. And we're going to have a buffer here of 2 blocks, okay? And then you're going to add 3 blocks to this. And so basically, it's a balanced line. They're both putting together 4 blocks, because this you could say this is 1 block, and then he's adding 3, so they both have 4 assemblies to the balance. And what we're going to do, we're going to introduce a yellow block to show the cycle time of how long the whole part takes to get through the system. Okay.
Yeah, but there are different terms for the cycle time or lead time. And that's very important because most often you want to make a promise to a customer that you're going to deliver something at a certain time. And you'd like that promise to be early so that the customer doesn't have to wait, but you also need that promise to be reliable. So we're going to look at that here. Okay, so
basically, we're going to start and run this for 2 minutes. The first.
Okay, so what is this? Okay, go ahead. You go ahead.
So the buffer, if the buffer becomes depleted, then she's start.
No, he's start.
blocked.
He's start.
He's-
No. If the buffer becomes empty, he's got to wait. He's got nothing to do. He reads a magazine or something. He's stuck. If the buffer becomes full, then she's stuck. She can't do anything.
I can only have 2 at a time. I can only have 2.
No, only 2 maximum in here. You produce 1 at a time. Okay? Oh, I see. Okay, so here's an example of the buffer being full.
Yes, we're going to start with the full.
Oh, we're going to start with the full buffer. Okay. So the issue here is to look at the difference between a 2-piece buffer and a 10-piece buffer. And what's particularly interesting for this is to look at the time that it takes for a part to get through the system. Okay? So, go ahead.
Okay, so we're gonna start with running the line, and this yellow block will represent the time it takes to get through the system. So this should make it through the buffer before we introduce a problem. We're gonna actually shut down the machine after 15 minutes.
Seconds.
Seconds?
We're going to use the yellow block as a marker, so that we can time when the yellow block goes in, and we can time when it comes out, to see the time that it takes for a part to go through the system.
So machine 1 is gonna break down in 15 seconds, and she's gonna be down for 30 seconds. And then machine 2 breaks down at 60 seconds, and he's also down for 30 seconds. It's kind of contrived, but it's going to illustrate. It's going to illustrate what happens with machine breakdowns and whether something gets stuck in the buffer. And you'll see that they're both. He's going to be stopped. She's going to be blocked because at one point there's not going to be anything left in the buffer.
Right. You have to wait until he starts. You can start right away as soon as we say go. When you take one part out of the buffer, now the buffer is not full, and then you can work. Okay? But when there are two in there, you can't.
And this works best too if your build is pretty much at a good pace, not slowly. Okay, it works much better if you build fast.
Yeah, see, okay, everybody gets competitive when he says that. We've got all the records from all the previous years. We'll see if we can beat them.
doing the yellow block, right?
Yeah, I'll keep the yellow block. I'll keep this.
That's
time
your
going.
first piece. You're gonna
To
assemble
start,
with
so
that.
that first piece represents one of your 4, okay?
So, you're going to time.
I'm gonna time the shutdowns, he's gonna time the open stage, he's gonna time the throughput.
Alright.
Should I start?
Yeah, so, okay, well, so the scenario is, you're gonna start with one yellow block, then there's a, machine 1 breaks at 15 and up to
Yep.
45, machine 2 down at 60 and up at 130, and you're gonna pick up a second yellow block at time 60, or we'll make sure you get it.
Yeah, we'll.
You just be a machine, they'll take care of it. All right, whenever you say go.
Ready? Ready? Go.
Go.
No, you just put on 2.
Oh, 2? 3.
Wait a minute. Oh, wait, stop.
Yeah.
Stop.
I have to drop from the right sides?
Yes, it's a first in, first out buffer.
Well, that's not, yeah, that is important. So, how many is he putting on, how many green pieces is he putting on?
3.
Oh, 3. Oh, I was wrong. Sorry. All right, so we're starting again?
First in, first out, yeah.
Go. Stop.
That's what part 1 was. Read a newspaper, you want to do it.
Park holidays.
Not yet. Go. But now with the yellow one.
I'm going on, you're on. No, go.
Stop. Pick up the yellow one.
Yeah, both have. No, yeah, that's right.
Yep.
Sometimes factory life is boring. The yellow's out.
That's the same. Level same.
Okay.
Yep.
Okay, so we got 5, 10, 12 parts. Okay, all right. This is not time. Let's decompose these things. There's no rush. There's no rush. Okay, now we're going to do exact same thing, except that now we're going to have a buffer of size 10.
Oh, there's a line.
That's what the line is. That's what the line is. What do you think is going to be the result of having a buffer of size 10?
No difference, because she's faster.
Okay. Anybody else have an idea?
Effectively, the irregularities should decrease.
We'll see.
So you're starting with the yellow.
Start with the yellow again.
Yep. Ready? Let's go.
Notice that he's able to keep working because of all that stuff that was in the buffer. It's also dangerous standing here while it's frozen. Notice also, now it took 60 seconds to get the yellow part through. So we've already made 12 parts. So that was, well, that we had the whole 2 minutes last time. So we're making a lot more stuff, but the lead time has gone up.
Go ahead. Stop.
Okay. So we have 17 products. Yeah.
That's my work.
And what about the timing?
And that didn't quite make it.
Oh,
It would have been about very close to the 1 minute.
where is it?
It's right there.
Oh, yeah, okay. So, it's very, very reproducible, that was good. Did the same thing in both minutes, we're not done yet, don't go away. So the consequence of the increased buffer space is increased production rate. But it comes at a cost, first of all, of having more, we have to pay for the inventory and we have to pay for the buffer space. And we also have an increased lead time as a result. Okay, so let's let's decompose everything. Notice how I'm keeping ahead of him. That's because my operation is easier. Okay, for this next story, we're going to use the yellow piece for a different purpose. Okay? This time the yellow piece represents a defect, a quality issue. So what's going to happen is that she's going to be doing her work very, very well until some point where something changes, her tool wears out or something, and not only is she going to make a bad part then, but because we don't know that the tool wore out, she's going to keep on making bad parts until we fix that tool. Do we ever fix it, or do we just make bad parts?
Yeah, once it gets into the cube.
Oh, that's right. Yeah, the problem is we can't fix the machine until we know that there's a problem. But the inspector is here, not there. So we don't know that there's a problem until we see the first yellow part come in. The first part with a yellow marker in it. So at that point, we discovered that there's a problem, and then we fix that machine. Okay? So we're going to see again the effect of a 2-piece buffer or a 12 or a 10-piece buffer. These guys know the times.
Yeah.
So you start making bad parts 5 seconds into it.
I'll tell you what. Should just keep going
Until we discover it, and then we'll probably going to start making good ones.
What is the overall size?
1.5.
2. Oh, it's 1. Okay.
We're running this for 1.5 minutes.
1.5. Okay.
Okay, ready? Go. Just keep using your...
Oh, sorry.
There it goes.
Okay, start making good ones now.
Okay, notice this was an instantaneous repair.
Stop.
Okay. So we've made 13 good pieces and 4 bad pieces. You want to- okay. Okay, did I count it right? Yes. All right. So, what do you think is going to happen this time? Yes. We'll see. Okay, anybody else have an idea? Same number of bad parts, fewer? What about the total production? All right, we'll see. We'll find out. We'll do the experiment. All right? Same time, same time.
Same time, 1.5 minutes.
So. Here we go. Start moving the go.
It's also a quality defense, so keep counting. And stop. Okay, we have 10 good pieces and 8 bad pieces. So that's interesting. The total number of pieces is about the same, isn't it? The reason that the total didn't change is that we didn't stop either one of the machines. We had this instantaneous repair. If the repair took time, then we would certainly see a difference, or we probably would see a difference. But notice also, somebody, you got it right. We made many more bad pieces this time, and there's many more that are still stuck in the buffer. So that's the other thing. The bigger buffer, the benefit is we get a higher production rate. The cost is that we have more inventory. We have more inventory space that has to be allocated for it. We have a longer lead time, and we have the danger of increased bad parts, so reduces quality. Okay. Any other questions? Any questions about this? All right. I guess you're fired. Okay. You guys want to take it apart? Or leave it? Yeah. Okay.
Thank you.
Okay, that was fun. Back to work though. Okay, so now we're going to take that and sort of look at some of the issues that we talked about there. I'm not going to have time to talk about quality. I'm not sure if I can go through everything I want, but we're going to talk about quantity-related things here. So here's our production line. Here in general is a multi-stage system. We have machines that are represented as squares and circles that are represented as buffers. The machines are going to be unreliable. Eventually, when we finish, the buffers are going to be finite. These are typically used for high volume, low variety production. So all the parts follow the same path through the system. If they're all identical, that's easy. If they're not identical, they may still have the same operations, but they're distinguished in some way other than by the operations, or maybe the operations are almost the same and there's some flexibility in the machines. But let's just focus on the total production, and we'll just think of it as a single product. The kinds of performance measures, we've already seen some of this. Production rate, inventory, lead time. We want to know the averages. Sometimes we want to look at variabilities like standard deviations or percentiles, but mostly we'll focus on the means today. Here's a simulation of the output from the output of a transfer line. The thing to notice about this is that on the vertical axis is the production in a week of simulated time, and this is about a 2-year period this way. This was based on factory data, but it wasn't just the same order of magnitude of the numbers that we got. The numbers that we were looking at, we've been assuming fixed and identical processing time, but different, but random failures and repairs. So the data that we used was the uptime and downtime. And you can see that there's a trend here, but there's a lot of variability around that. Trend. Okay. So you can say that this is going to produce an average of 3,000 parts a week, but if you have a factory downstream, these were making parts, car parts, engine parts. So they're eventually going to get assembled into an engine, which is eventually going to get assembled into a car. But if the factory next door is expecting these parts at a constant rate of 3,000 a week, it's going to be very disappointed, because half the time or so it's below that, and half the time it's above. So somehow you're going to need a buffer between this production line and the next one to smooth out that variability. Otherwise, the second one is going to be waiting a lot. So I'm going to go through a sequence of examples. I'm going to start with the single reliable machine, which is trivially easy to understand. And then I'm going to make it more and more complicated until I completely boggle your minds. So if the machine is perfectly reliable, its average operation time is tau, then its maximum production rate is 1 over tau. That's easy. So you can use that machine to produce parts at a rate of 1 over tau or less. Okay. So now let's make the machine unreliable. And the parameters that we need are the mean time to fail and the mean time to repair. And the mean time between failures is just the mean time to fail plus the mean time to repair. So here's a formula which I will proceed to prove on the next slide. If the average operation time is tau like before, the mean time to fail is MTTF, the mean time to repair is MTTR, then its maximum production rate is going to be this, where we define E as the efficiency. I mentioned efficiency earlier, so that's the fraction of time that the machine is available for production. So it's either working or it's under repair. So here's the maximum production rate. So it's reduced from before because of the downtime. Okay, so here's a little easy mathematics. Here's how the machine behaves. During the green bars, the green intervals, this is a timeline. During the green bars, it's up, and during the red bars, it's down. So the average production rate while the machine is up is 1 over tau, because tau is the operation time. The average duration of an up period is MTTF. So the average production during an up period is MTTF divided by tau. That's easy. So that's just an average green bar. Now let's look at a green bar and a red bar together. The average duration of an up-down period is just MTTF plus MTTR. The average production during an up-down period is still MTTF over tau, because we don't produce anything during the red period, during the down period. So it's the same, this number is the same as this number. So the average production rate is MTTF over tau divided by MTTF divided by MTTR, which is just the formula that I showed you before. Okay? So you can think of the efficiency as representing the fraction of this line that's green. Okay. Here's another Markov chain model, which is much simpler than before. I'm not going to take you through this in any sort of detail. But here we have two states, up and down. And when the machine is in the upstate, it could stay up with probability 1 minus p, or go down with probability p. And the same thing when it's down, it could stay down or go up. And from that, well, the relationship between P and R and the mean time to fail and mean time to repair look like this, so the efficiency is given by that formula. Okay, so we did two cases now, a single machine, a single reliable machine and a single unreliable machine. Now I'm going to look at a whole line with infinite buffers. That's the next easiest case. So what happens now is that if machine 2, for example, fails, machine 3 can operate as long as there's material in buffer 2. But if machine 2 fails long enough, buffer 2 is going to become empty, and then machine 3 is starved. Okay? So we're assuming that a machine is not idle if it's not starved. In other words, it works whenever it can, and the first machine is never starved. And the bottom line of this is that the production rate of the line is the production rate of the slowest machine in the line, which is called the bottleneck. So here's machine 5. So by slowest, I mean the least. I said that on the next slide. But it's the machine that has the least production rate. Okay? All right, so that's there. Okay? So the production rate of the line is the production rate of the slowest machine in the line. Okay? What about the inventory? Anything interesting to say about the inventory? All right, I'll tell you. So here's the formula for the production rate, where machine I is the bottleneck. Now let's look at machine 5 is the bottleneck. Let's look at what happens in buffer 4. What's going to happen is that we're going to see that there's going to be an infinite amount of inventory accumulating in this buffer. And here's a simulation. So this line, so here's the vertical axis is the number of parts in the buffer, the horizontal axis is the time. This one is the 9 machine line, with machine 10 being the bottleneck. And so all these other buffers, go up and down, but don't leave, don't get too far from 0, whereas this one is going up. It looks like it's kind of a straight line. And what's happening is that we have all these parts that are flowing through, but when they get to machine 10, they're forced to wait because machine 10 is down a lot more than the others, so they accumulate in buffer 9. And so that's why this is increasing like that. Now, it's an infinite buffer, so if you wait long enough, you'll have an infinite amount of inventory. But what's more important is that machine 9 is not affected by the failures of machine 10 because the buffer is infinite. Okay? So the next thing we're going to look at is what happens when the buffer is finite. Okay? Everybody see this picture here? Everybody got it? Okay. Questions? Okay. Well, so here's a question. Questions. If we want to increase the production rate, which machine should we improve? And what would happen to the production rate if we improved any other machine? What do you think? Yes?
I mean, you want to improve machine number 10?
The bottleneck. Right. That's right. And what happens if I improve anything else?
It's not going to help.
Won't do a thing. That's exactly right. Okay. Now let's go to the other extreme. 0 buffers. Okay? No buffer space. So what's happening here is that if any one of these machines fails, essentially the others stop instantaneously. Okay? So we can imagine that this is going to be very different from the infinite buffer case. In fact, the production rate is going to be much less in most cases than the slowest machine in the line. So let's look at it. Well, I'm going to make these assumptions so that I can show you a formula. I've already defined the P and the R this way. And the formula is this. Here's the production. Oh, I forgot to say, just to make life a little bit easier, I'm going to assume that tau equals 1 from now on. Okay? So you can say that this is the production rate per operation time. In any case, here's the production rate of the line. And if I had only one machine, if K were equal to 1, then if you multiply the top and bottom by R, that reduces to the formula that we had before. So it's the same thing. But when we have more terms, then, if we have more machines, then it looks like this. So the more machines you have, the lower the production rate. Also, what's interesting to me is that the P is a function of the ratio, P over R or MTTR over MTTS. And the same thing is true for the infinite buffer line, because the production rate is just the production rate of the worst machine, which is also a function of that ratio. But this statement is not true for a line with finite non-zero buffers. In other words, it's not a function of just the ratio, it's a function of the P's and the R's separately. Okay, so here's a question. If we want to increase the production rate, which machine should we improve? And what would happen to the production rate if we improved any other machine?